Hello, these are the conservation of energy example problems from Unit 3 for AP Physics 1. So we begin with the falling rock problem here, where at the beginning I am holding a rock above the ground. And as far as its energy is concerned, it is completely potential energy. And that is at some height that is given to be 3 meters. And they say that's y1. So let's just write that to the side. y1 is equal to 3 meters. Then as I drop it halfway down, my potential and kinetic energies have exchanged somewhat, and halfway down I am half potential energy and half kinetic energy. Once it reaches the bottom, right before it hits the ground, it is completely in the form of kinetic energy. And this is at a final y of 0. Now, we want to know the velocity when it has fallen to 1 meter above the ground. So this would be the case where it's somewhat about right here, where y2 is actually 1 meter above the ground. So we are going to set up a problem-solving process for all of our conservation of energy problems that begins with a statement of the conservation of energy. And so that is K1, so kinetic 1, plus gravitational potential energy 1, plus elastic potential energy 1, plus any work done by friction or other forces, and that's equal to kinetic energy 2, so our final kinetic energy, plus gravitational potential energy 1, plus elastic potential energy 1. So once we start with this statement of conservation of energy, we're going to go through one at a time and decide if any of these are 0. So initially, if I'm going to drop a rock, I start off, and there's 0 kinetic energy, it even says here, I start off just at rest. So initially, I have 0 kinetic energy. As it indicates in this drawing, or diagram, I have a lot of, or completely, gravitational potential energy. So this is not 0. My elastic potential energy is 0. There's no mention of a spring or anything that is elastic here. There's no mention of friction or any other work, so this term is 0. Right before it hits the ground, as this diagram indicates, we have a lot of kinetic energy, and we have essentially a smaller amount of gravitational potential energy, because we have a lower height. And then again, we have 0 elastic potential energy. So we've simplified this down to the following. So I have UG1, so that's mass times G times Y1, is equal to 1/2 mass times my velocity at point 2. So point 2 is about right here. We'll call this 2. Plus mass times G times Y2. I apologize, this should be a 2. So should this. And so we're looking for velocity at this point. So let's rearrange this after we make a simplification. All of these terms have a mass in it, so let's cancel those out. Now I'll subtract gy2 from the left side. So I have gy1 minus gy2. Then I'm going to multiply both sides by 2 to get rid of this 1/2. And that means that v2 squared is equal to this. Or v2 is equal to the square root of that. So my final step here is going to be the square root of 2 times, so this is 10 times y1, which was 3, minus 10 times y2, which was just 1. Close those parentheses and square root all of this, and we get our answer where this velocity is approximately the square root of 40, or 6.3 meters per second. So again, the problem-solving process we're outlining here is start with conservation of energy, simplify it, and get something simpler where we've substituted in the remainder of our equations. So this right here is conservation of energy. This is our simplification step. This step, our next step, is to solve algebraically. And then finally, we substitute and get an answer. And that is what we have for this first conservation of energy problem. And we will repeat this process for pretty much every conservation of energy problem. For our second example problem, we have a roller coaster, and we're looking to calculate the speed of the roller coaster at the bottom of the hill, which is given to be right here. And so we start at some position y above this bottom hill. So we can say that this, our lowest point is our 0 location, and this point where we start is some y, which was given to be 40 meters above the hill. And so this is actually not just y, but y1. So we're going to start, like we did with our previous problem, with a statement of conservation of energy. So K1 plus UG1 plus UE1 plus work is equal to K2 plus UG2 plus UE2. And then we're going to go through one at a time and decide if any of these are 0. So let's start with the fact there are no springs here. So this elastic potential and this elastic potential energy are 0. There's also no mention in our problem statement of friction or any other force, so we'll say that work is also 0. Now initially, it says that we are starting from rest at the top. That means that our initial kinetic energy is 0 because our V1 is 0. We have, therefore, some gravitational potential energy to begin with. Otherwise, we wouldn't go anywhere. And then at the bottom of the hill, we know that we're going to be moving at some point since we're looking for speed. And we've set this to be 0 as far as our height is concerned. So our final gravitational potential energy is 0. So let's go ahead and simplify this. So instead of UG1, I'm going to write m times g times y1. Instead of kinetic energy 2, I'm going to write 1/2 m times velocity 2 squared. So let's zoom in. So now we have a case where mass is in both terms, so let's get rid of that mass. And let's solve this for V2. So I'm going to move it to the left. I'm going to multiply by 2. So I have 2 times g times y1, and then I'm going to square root. So my velocity 2 is just 2 times g times y1 all square rooted. So let's substitute in some values. V2 is the square root of 2 times 10 times our initial height of 40 meters. And so velocity 2 is just going to be 28.3, we'll round it to, meters per second. Now, that's part A. Part B says, at what height would it have half of that speed? So let's work backwards. So B asks us, what about half of the speed? So V2 was 28.3. Half of that, so we'll say this is V2B, is 28.3 divided by 2, which is, we'll say 14.1 meters per second. And so now what we want to do is we want to go work backwards. So we know that we'll have the same statement, which would be mgy1 equals 1/2 mv2 squared. And so this is V2b. So mass cancels again. And in this case, we're looking for y1. So we have y1 is 1/2 times V2b squared over g. So let's substitute in some numbers. 1/2 times our 14.1 squared over 10 gives us an initial height of, we'll say, pretty much 10 meters. And so there you have it. Same conservation of energy concepts, just applied in a slightly different way. For our third example problem, we have two different water slides that have different shapes. They start at the same height, they end at the same height. However, as we said, they have different shapes in between. So the question is, which rider, Paul or Corinne, is traveling faster at the bottom? So since they have the same heights, let's actually just start by stating conservation of energy real quick. So K1 plus UG1 plus UE1 plus work done by other forces is equal to K2 plus UG2 plus UE2. So we see then that initially we're going to start from rest, as it says here, and we're going to have some speed at the bottom. Initially we'll have some height, and no springs are mentioned, so our elastic potential energies are 0. No work done by extra forces, and at the bottom we have no gravitational potential energy remaining. So in this case, we simply have m times g times y1 equals 1/2 m times v2 squared. Now, regardless of who we're talking about, mass ends up canceling out. And so what we see now is that our speed at the bottom is simply going to be the square root of 2 times g times the initial height, h. So both Paul and Corinne will be traveling at the same speed at the bottom, because the shape does not matter in this case. Now, which one will make it to the bottom first? Ooh, this is a tough one. So how do we decide this? Now we have to actually look and see the path that these guys are traveling. So if you take a look at this, you see that Corinne is consistently lower than Paul for the entire trip. So even though they start and end at the same place, Corinne has transferred her energy to kinetic energy for the majority of the trip compared to Paul. Therefore, she is traveling faster than Paul for the majority of the trip and will reach the bottom first. So we'll say Corinne, because more kinetic energy for majority of the trip. And there you go. So we have an interesting situation where we used conservation of energy to prove they both get there with the same speed at the bottom. However, when we talk about getting there at the same time, then we need to spend a little bit more effort and think, okay, for how much of this path are we traveling at a higher speed? And we do that by thinking about, okay, lower altitude means more kinetic energy that we've translated from potential energy. And there you have it. For our next example, example 610, we have a toy dart gun that uses a spring to launch a dart. So the mass of this dart is given to be 0.1 kilograms. That's the only mass we care about. Initially, it's given that this dart has an initial speed of 0. And the spring constant, which is constant throughout the entire problem, is 250 newtons per meter. It's compressed a distance of 6 centimeters, so we're going to go ahead and write this compression distance, x1, is equal to 6 centimeters, which we want to be in meters, so that's 0.06 meters. So let's go ahead and begin by writing out our conservation of energy. Oh, and we'll say that x2, when it's uncompressed, is 0. So we'll start by writing our conservation of energy. So we have K1 plus UG1 plus UE1 plus work done by outside forces is equal to K2 plus UG2 plus UE2. So one at a time, let's eliminate some things. Initially, we are not moving, so our initial kinetic energy is 0. Our gravitational potential energies, what do we see here? Well, if we launch our dart horizontally, then you see that our height is not going to change. So if we think about this for a second, let's see. UG1 and UG2 are both mg times y, so we'll say mgy1. And then if I want to move that over, just for argument's sake, mgy2. Well, if y1 is equal to y2, then this is just equal to 0. So we can just say that these two would cancel each other out, whatever height we're at. Now, there's no work done by any outside forces, and after our spring is launching our dart, it is not compressed anymore. So our final elastic potential energy is 0. So all we have now is elastic potential energy and kinetic energy. So we have 1/2 times k times x1 squared equals 1/2 times mass times velocity 2 squared. So simplification allows us to get rid of our 1/2, and we're going to be solving for V2. So V2, just divide by mass and square root, is going to be, so we divide by mass, k over m times x1 squared, and then we square root. V2 will end up being, once we substitute, 250 divided by 0.1 times 0.06 squared. So be careful here. This is sometimes tricky to put in your calculator. And when you do that, you get plus or minus 3 meters per second. But since we're asking for speed, we're just going to say 3 meters per second. So there you go. That's the speed that our dart acquires, and all we had to do was use conservation of energy. For our next example, we have a vertical spring. Now this is where it starts to get a little interesting. So first we have a ball that falls a vertical distance of 55 centimeters. So we're going to go ahead and say that y1 is 55 centimeters, which we're going to convert to meters, and so that's 0.55 meters. Now, it strikes a coiled spring, which compresses it an additional 15 centimeters. So we're going to go ahead and say that y3, as it's labeled here, is negative 15 centimeters. Or we can write that as negative 0.15 meters. Sorry if you can't see the point. There we go. And we want to determine K for this. Ooh, there's the answer there. So the ball itself has a mass m, which is given as 2.6 kilograms. And now we want to go through our conservation of energy to determine this spring constant K. So let's start with that statement of conservation of energy. K1 plus Ug1 plus Ue1 plus work is equal to K2 plus Ug2 plus Ue2. Now, the problem states that the ball is dropped from this height. So dropping implies that our initial kinetic energy is 0. Similarly, if we want to know the maximum compression of our spring, that means that our ball has pushed it as far down as it will go before it starts going back up and decompressing. So that means that our very bottom, our ball is going to be changing directions and therefore will not be moving for that instant. So we have a kinetic energy of 0. Now it says ignore air resistance, so there's no work done by additional forces. Initially, we have definitely some height because we're falling, and we have 0 elastic potential energy because our spring is unstretched or compressed to begin with. So now we have our gravitational potential energy final, which we're going to have something because we have a negative displacement here. And our spring is compressed, so we'll have some elastic potential energy. So let's zoom in and expand this. So we have m times g times y1 for our initial gravitational potential energy. Then we have m times g times y2 for our final gravitational potential energy. And then we have 1/2 k times x2 squared for our elastic potential energy. And there are no other simplifications we can make, so at this point we just need to solve for k. So I'm going to put k on the left here, and what we have is, so I'm going to subtract mg y2, so that's mg y2, and then I'm going to multiply both sides by 2 and divide both sides by k. I'm sorry, not k, by x2 squared. And that'll give us our k. So let's substitute some values. So we have 2 times our 2.6 kilograms times, I'm going to go ahead and write 10, times y1, which was 0.55, let's go ahead and write 0.55 for clarity's sake, meters, minus 2.6 times 10 times our final y position, which is negative 0.15 meters, add some parentheses just to make sure, all over our displacement of the spring, which from 0 to the negative 0.15 is just negative 0.15. Don't forget to square it. So plug all this into your calculator and go slow, and you find that k is equal to, I get 1,618, so let's go ahead and round that to 620, and the units here are going to be newtons per meter. So there you have it. A vertical spring is a little bit more complicated because you can't cancel out mass or anything else. And so you simply have to be aware that you have some initial gravitational potential, you have a final gravitational potential, and you have an elastic potential. Now you could just as easily do this as we did in our previous example in class, where you set the lowest possible height as 0. But you need to be aware exactly what's going on when you talk about your displacement. So be very careful when you do that. For our final example, we have friction finally included. And so let's just start off without knowing anything more about the problem by writing our conservation of energy statement. So go through the process, include work, kinetic energy, gravitational potential energy, and elastic potential energy. And now let's read the problem. So we have a roller coaster car and it reaches only a height of 25 meters. Uh-oh. It traveled a total distance of 400 meters. Okay, so this total distance is 400 meters. And we want to determine the thermal energy produced. So remember we said that when friction does work on something, it turns that energy into energy we can't use anymore. That energy typically gets lost as heat, or something hot, and so we call that thermal energy, and it goes to where we can't use it any longer. So now we want to assume that this energy is getting lost because of friction, and we want to figure out what that friction force is. So the mass of our car is 1,000 kilograms, and as it says, we travel a distance of 400 meters. We start at a height of 40 meters, and we end at a height of 25 meters. So y1 is given to be 40 meters, and y2 is given to be 25 meters. So once we go through our conservation of energy statement, let's see what we have. So it's initially at rest. At our initial height, we have some gravitational potential. There are no springs. There is friction in this case. Then once we get to our second location, it slows to a momentary stop. So it stops when we get to 2. So that means our kinetic energy is 0 again. Then we have a gravitational potential because we have an initial height, and our elastic potential energy is 0 because there's no spring. So let's go ahead and write out all of the pieces to this. So gravitational potential energy 1 is mg times y1. Our work is our force of friction times S. And then our gravitational potential energy final is mgy2. So let's rearrange this to solve for the force of friction. So the force of friction is going to be mgy2 minus mgy1, right? We just subtract that. And then we divide all of this by our displacement S. So now let's substitute. So we have a mass of 1,000 kilograms times our g of 10 times our final height of 25 minus our mass 1,000 again times 10 times our initial height of 40 all over our complete distance traveled of 400 meters. So the force of friction in this case works out to be negative 375 newtons. Now, looking at this, I actually realized that we should have determined the thermal energy produced first instead of finding the friction. But that's easy because we can back up a second. So if we look at this and we just want to know the thermal energy produced, we want to know the work done by friction, which is going to be the change in our potential energies. So that'll be mgy2 minus mgy1. And so going through this process, we can actually just take our force that we already found and multiply by 400 to get it. And we see that our work done by friction in this case is negative 150,000 joules. And of course, it's negative because friction is taking energy out of our system. That's why our roller coaster doesn't quite get as high up on the hill.